Now we turn to searching. Let's quickly recap the two ways to find a value in an array and see why sorting makes the fast one possible. Linear search is the search that always works. It does not care if the array is sorted or not. You just look at every slot until you find what you want. Here we search for the value 23. Each row is one probe and the rows stay. Probe 1, index 0. I at index 0 is 2. 2 is not 23, so no match. We move on. Probe 2, index 1. I at index 1 is 5, still no match. Probe 3, index 2. I at index 2 is 8, no match. Probe 4, index 3. I at index 3 is 12, no match. Probe 5, index 4. I at index 4 is 16, no match yet. Probe 6, index 5. A at index 5 is 23. That is a match. We return index 5. It took 6 probes to reach it. Here is linear search in C. It takes the array, its size, and the key you want, and it returns an index. The loop scans every slot, from 0 up to n-1. At each slot it compares against the key. On a match it returns the index straight away, so it stops early. And if the loop falls off the end, the key is absent, so it returns -1. There is no pseudocode for this one, deliberately. Textbook pseudocode would be a near verbatim copy of this loop. The cost is big O of 1 in the best case, if the key is first, and big O of n on average and in the worst case. The one thing worth noticing, it needs no ordering at all. When the data is sorted, you can do something much better. Binary search throws away half of the remaining values on every single comparison. Let's read the pseudocode. We set low to 0 and high to n-1. Those two bounds mark the interval we are still searching. The loop runs while low is less than or equal to high. We compute mid, the middle index. If A at index mid is equal to the key, we found it, so we return mid. If A at index mid is less than the key, the answer must be to the right, so we move low to mid +1. Otherwise it is to the left, so we move high to mid -1. If the interval empties out, we return nil, meaning absent. And here is binary search in C, matching that pseudocode. Low starts at 0, high at n-1. Those two together are the interval we are still searching. The loop runs while low is less than or equal to high, that is, while the interval is not empty. We compute the middle as low plus, high minus low over 2. Written this way it cannot overflow, even on very large indices. If A at mid equals the key, we found it. If A at mid is less than the key must be to the right, so low moves to mid +1. Otherwise it is to the left, so high moves to mid -1. Either way, half the interval is gone. And when the interval empties, we return -1. Note the comment. -1 is an index sentinel, not null. Binary search costs big O of log n, but read the condition attached to it. It requires a sorted array. And that requirement is exactly what the rest of this chapter builds toward. One note on sentinels from chapter 2. An index search returns -1, not null. Null is reserved for the operations that return a pointer,